I created a classification learning model that can predict the types of movements you make using EEG data, and I did all of this using no code. First, I had to power up MATLAB, a powerful tool that allows users to analyze and design data systems. Once I have that loaded up, I have to import my EEG dataset, which I got from Kaggle. This dataset contains information from different channels in my EEG, each respectively collecting electrical signals from the neurons of the patients that produce electrical signals for each specific task. In this case, I chose to focus on 4 major motor functions for the simplicity's sake of this video. Them being your left hand movement, right hand movement, tongue, and foot. Also note, I will only be using one patient's dataset, and that alone will almost take more than 57,000 plus rows. Talk about data richness. Once we have that in place, we will have to make sure our label column is in categorical format, which will be vital later on in the process. Then we have to filter out the unwanted data that will ultimately affect the quality of our training. For example, we don't really need the patient number. A, because we're only using one patient. B, because it doesn't really affect the outcome of the electrical signals we derived. So I say we need data from column C, excluding the first row, to Z, and I'm going to take about 37,000 rows because it makes the training a little simpler. We are going to import that data into our workspace now, so we can open up a powerful app embedded in MATLAB called a classification learner. This app trains models to classify data using supervised machine learning. Now remember in a previous step I said we had to make the label into a categorical format? Yeah, that's important now, because MATLAB already recognizes there are 4 unique categories it has to classify. Now I'm going to use the holdout validation as my validation method, as our dataset is quite large and the holdout validation method is optimized for large datasets. And I would say you would need a holdout percentage of 20, and that's just a personal preference. I found it works best for my dataset, but do play around with it in your own time. Next, you have to select a model that you would like to use. I chose the optimized KNN model as it's commonly used for classification, since it uses a proximity to make classifications working off the assumption that similar points can be found near one another. We use this optimized version because it adjusts the hyperparameters towards a higher percentage for accuracy while testing. Once we have that selected, let's go ahead and make our iterations to about 50, since we don't want our training to finish prematurely, do we? And all we gotta do now is hit that train button. While this model is training, I want to elaborate a little bit on why this is important in the first place. Well, in the world of brain-computer interfaces, classification is one of the major steps that allow for magic like this to happen. Now that you've experienced the magic of brain-computer interfaces, let's talk about the 4 major steps that actually involve making this process possible. The first step is signal acquisition. This means how you get the raw signal from your brain. This could include EEGs, ECOGs, fMRIs, and so on. So once you take this raw signal from your brain, the second step, you get to identify features you would like to classify. So this means taking a messy frequency and then decomposing it through a system such as the fast Fourier transform, and then putting into different bandwidths, then identifying features you'd like to classify onto the third step. The third step being classification. So this is what we're developing through our model, which classifies motor functions such as right hand movement, left hand movement, and so on. So taking these classified features, you get to output it into devices. This is the special part, because this allows for patients that suffer from motor degenerative diseases to feature a function they were exempted from their whole life. So keeping this in mind, let's go back and look at what has resulted in our model. So what exactly are you seeing here? Well, it's a minimum classification error plot. This plot basically visualizes how the model is optimizing the hyperparameters so it can go towards a higher accuracy as each iteration goes by. In a couple of seconds, you can see how we have reached a high accuracy, and hopefully, in a couple of seconds, you can see that we're going to reach an accuracy level of 100. And at this point, once the iterations are finished, you can go ahead and deploy this model if need be.